This recording is for Chapter 4, Section 3 on conics. If everybody would please open up your textbooks to page 329 and get out your notebook, we will begin. So I decided to put a few vocab words up here. The first one up here deals with conics in general, and it says that the conic is an intersection of a plane and a double napped cone. Well, I had never heard of what double napped was before, so I looked at the picture, and a double napped cone looks kind of like an hourglass shaped thing. So a conic is going to be, if we were to slice through that cone in some place, what would that intersection look like? Okay, so the second word, degenerate conic, is when the plane passes through the origin. And then a locus, we're going to hear that word from time to time. A locus is simply a collection of points. Now, we've talked about parabolas quite a bit, so we're not going to spend a whole lot of extra time on them. You know what the shape generally looks like. We know that they graph a quadratic function. We know that parabolas are symmetrical. Reference points of a parabola, so our keywords that we need to learn or know. Number one, the vertex. We already know what that is. Technically, we already know how to find that vertex point in a couple of different ways. Number two, directrix. And three, focus. Those might be a little bit review from last year, but we have not talked about them yet this year. And then point number four is the axis of the parabola, or the axis of symmetry. That we've already been working with. Standard equations of a parabola. Parabolas with a vertical axis of symmetry and a vertex at 0, 0. The standard form is going to be x squared equals 4py. Now, the directrix is going to be equal to y equals negative p. It's going to be an equation of the line. It's going to be a y equals line, and we're going to find that by taking negative p from the standard form. We'll talk about that more in a second. Or, number two, parabolas that have a horizontal axis of symmetry and a vertex at 0, 0 will take on the form y squared equals 4px, where the directrix will be x is equal to negative p. So your directrix is going to be an x equals line if you have a y squared parabola equation. The reason for that is when our parabola equations begin with y squared instead of having an x squared in them like we've mostly been working with so far, the y squared parabolas are going to tip to the left or to the right. Finding the standard equation of a parabola. Now, if you're given the focus point, 0p, okay, put the number that is p back into y squared equals 4ps, or 4px. If the focus point is 0p, that means that parabola is going to open to the left or to the right. We'll see that in a second here again. Number two, if you're given a focus point p0, that means the parabola is going to open up or down, and then we're going to plug p back into the x squared version of the standard form of a parabola. X squared equals 4py. Once you have put the p-value back in, you're going to simplify by multiplying that by 4, and then you'll have your equation that you're looking for. All right, so we have to be able to recognize whether our parabola is up and down, or if it's going to be a left or a right. And we'll be able to tell that by looking at how our focus point comes to us. Now, to find the focus in the directrix of a parabola, I put a bunch of steps up here. Hopefully they will make sense. The focus of our parabola is a point that's not on the curve. All right, so if you take a look at some of the pictures that are in our textbook right around page 330, page 331, look at any of those diagrams and notice that each of them has this focus point. Now, one of the things that I'll be talking through with these steps here is, we've mentioned directrix, we've mentioned focus. If, for example, you're looking with me at the top of page 330, the directrix line is dashed in there for us, and the focus point is plotted. Those two things are the exact same distance from the vertex. So if the focus is 2 units above the vertex, the directrix line is going to be found 2 units below. Okay, so back to our slide here. Step number 1 for finding the focus and directory is to rewrite the function by isolating the squared term on the left-hand side. Okay, so however the function comes to you, isolate or rearrange it so the squared term is on the left, everything else is on the right. The right-hand side is going to have a number with it. Rewrite the number part on the right side as the product of 4 and something else. The amount that is multiplied with the 4 is p. The focus of the parabola, I'm on step 4 now, the focus of the parabola is 0p for parabolas that open up or down. It's going to be p0 for parabolas that open left or right. The directrix of the parabola is either x equals negative p or y equals negative p, depending on if the parabola is upright or facing left or right. We just talked about that on the previous slide. The vertex is directly in the middle between the focus and directrix. So things that I was talking about with the last slide and what I was talking about with you looking at page 330 in the book, all of that is summarized on this slide. So for checkpoint number 1, let's find the focus and directrix of the parabola y is equal to 1/4 x squared. Then sketch the parabola. So the first thing, when I look at this one, I notice that I have a y equals 1/4 x squared parabola. With an x squared term in it, we know this one's going to open up. And I know it's up versus down because my coefficient of the x squared is positive. So that's something that we are all familiar with. But this parabola is going to open up. That means the standard form of our equation can be found by getting x squared alone. So solving for x squared, if I multiply both sides by 4, I get x squared is equal to 4y. Now we want to rewrite that right-hand side so that it is in the form of 4 times another number. Well, since there is a 4 in there, the only way to rewrite this then as a product of 4 and something is to go 4 times 1. So p, our p value that we're looking for our focus, is 1. Since this was an up opening parabola, that focus point is going to be the point 0, 1. Our directrix, so that line, is going to be the y equals negative p, which then turns into y equals negative 1. Now, let's go ahead and plot our focus point, 0, 1, and draw in or sketch in our directrix line, which is y equals negative 1. Remember that the vertex of our parabola is directly in between the focus and that directrix line. So if I didn't know it already, which actually I did looking at my first equation, I know that my vertex is in between them at 0, 0. Okay? Most all of you could see that up here. If we ran our negative b over 2a, we'd end up with 0 over 2a, or 0. And we'd plug 0 in and get 0 again. So we could find the vertex in a couple of different ways. But I was able to look at my focus, I was able to look at my directrix, and the vertex is in between them. So let's come up with a couple of other values for a table. If 0 is the x value of my vertex, I'm going to go to both sides of it a couple of times. If I put in 1, actually I want to choose a couple different numbers. I forgot that this was a times by 1/4, so let me change my mind here. If I put in a 2, then when I square 2, I can times by 1/4 and get a whole number. So putting in 2, I get out of 1. Putting in a negative 2, I will as well. Then I'm going to skip 3. I'm not going to use that one. I'm going to go with 4 and negative 4 for the same reason. If I put that in and square it, I get 16. 16 times 1/4 works out evenly. So I'm going to get 4s for both of them. So 2, 1 and negative 2, 1. And 4, 4 and negative 4, 4 are a couple more points for our parabola. Now we could have gotten a pretty good general idea of how to sketch this parabola also if we'd have thought back to our transformations. This one had a multiply by 1/4, which was that vertical shrink. So we knew it was going to be the general form of our parent function x squared, but it was going to be a little fatter, a little bit wider. So keep trying to bring back those old things to help you figure out whether or not you're on the right track. All right, our other shape, one of our other shapes is ellipses. Ellipses are the set of all points in a plane whose distances from two distinct fixed points is constant. Now, the diagram in your book, I think it was in our book here, or did I look that up online? Nope, the diagram in the book kind of does this. If we were to put a tack on both of the focus points that I have here, and then attach a string to them and circle a pencil in it. So if we had that string, maybe here's our pencil, and the other string is attached to here, and we just kept moving, that would give us, or end up tracing for us, this shape of this ellipse. Okay, so that set of all points in a plane whose distance from two distinct fixed points is constant, that's going to end up generating this ellipse shape on our page here. All right, so take a look at this for a couple of seconds with me. We have some A's, some B's, and some C's. These are going to be very important for us to understand what they all mean. A's, so this point here and this point here, where the major axis, okay, there's two axes here. You've got the longest one, that's called the major axis, and then you have a shorter one called the minor axis. The major axis is always the longer one, the minor axis is always the shorter one. You may end up with ellipses that sit like this. Then the major is this one and the minor is this one. So the major axis isn't always horizontal, sometimes it's vertical. It all depends on the shape or the way your ellipse is sitting. Major is always longest, minor is always shortest. Now, the intersection points of the ellipse and the major axis are the points negative A0 and A0. The intersection points of the minor axis and the ellipse itself are 0B and 0 negative B. The focus, okay, the focus points are C values from the center of the ellipse. Okay. When we're trying to find a standard form of the equation of ellipse, these things are all going to come into play to help us with that. So the standard form of the equation of an ellipse centered at the origin with major and minor axes of lengths 2a and 2b. Now to understand that a little bit, let's go back. Do you see that this is length A and so is this? So the length of the whole thing is 2a. The length of this is B and B, so the length of this one is 2b. All right? So if the center of our ellipse has points A away and A away in two directions, that's where the 2a comes from, and then the 2b comes from the other direction. All right, so let's go back. So back to major and minor axes of lengths 2a and 2b. If the major axis is horizontal, this one is the format that we use. If the major axis is vertical, this is the one that we need to use. Notice that they're very similar. We just trade positions where the b squared and the a squared sit. The top one I already said. The middle one, the vertices and foci are always on the major axis. Okay, so the vertices are always those intersection points of the major axis, never the minor. A, B, and C have a relation. Okay, those distances of the vertice points, the intersections of the minor axis, and then those foci points, it's always c squared is equal to a squared minus b squared. So when we're finding the standard equation of an ellipse, identify your foci. Those give you your number c. Look to see the length of the major axis. Half of that distance is going to be one of your a's. Use the values of a and c to solve for b. Number 4, write the standard equation using the a and b that were found. All right, so let's give this a try. So find the standard form of the equation of the ellipse that has a major axis of length 10 and a foci at 0, negative 3, and 0, positive 3. All right, so remember our foci provide us with our C value. So C is equal to 3. If your foci are at 0, -3, and 0, +3, they are distance of 3 from your center. Our major axis has a length of 10. Now that's from end to end on the ellipse. We're looking for just A, not 2A. So if the whole length of the axis is 10, the length of A must be 5 or half of that. So we have A and we have C. We can use that equation on our previous slide to find B. So plug in what we know into this relationship. We have 3 squared is equal to, 5 squared minus B squared. So 3 squared equals, or 9, excuse me, we can go right to 9 now. Hold on. 9 equals 25 minus B squared. I'm going to move B squared over here, and I'm going to subtract 9 from both sides and get 16. So B is equal to plus or minus 4. So B is 4. Now we have what we need to make our problem. Now looking at 0, -3, because of the order of my foci, I know that my major axis was vertical. If it was horizontal, it would have gone like this instead. So being the foci was at the point, you know, if you think about this, or if we quick sketch it, 0, -3 and 0, +3 are here. We know that the foci and the vertex are always on the major axis. So if this one's the major one, our ellipse is going to have to sit like this. All right, so that's why I know that it's going to be 0, oh shoot, come back, 0, I went backwards. 0, -3 and 0, 3. Sorry about that. So we have to be vertical. I said vertical and then I tried to prove that it was horizontal. Sorry about that, guys. So being our foci are on a vertical line, we know that our ellipse is going to sit like this. All right, so I think I'm back on square now. So that means if it's vertical, the form of our standard is going to be like this. So plug in our values that we just solved for. And we're done. The standard form of the equation, they actually do not encourage you or suggest that you go ahead and simplify that to 16 and 25, because if we were going to graph this ellipse, we would need that A and that B. So where we leave them in this form, we can still see them. All right, let's sketch this one. So first of all, we have 4x squared plus y squared equals 64. Now in the standard form of an ellipse, this needs to be 1. So in order to get that to be a 1, let's divide everything by 64. So now I get x squared over 16 plus y squared over 64 is equal to 1. Rewriting that in that standard form, we've got x squared over 4 squared plus y squared over 8 squared equals 1. Now, with this particular formatting, when we're looking at the A and B, do you remember how A was on our major axis and B was always our minor axis? This front number here, would you agree, is smaller than this one here? So that one has to be B. And if that one is B, then I'm looking at the standard form x squared over b squared plus y squared over a squared. Would you agree? Okay, so that means if it's in this form, we must be looking at a vertical ellipse. All right, So this tells me then that B is 4 and A is 8. So I can go ahead, if this is going to be a vertical ellipse with A of 8, I know I've got this point here and this point here that I can graph. If B is 4, I can go ahead and go 4 away from my center for that. And all I need to do now is send my sketch through, and I have my ellipse. The focus, let's just do this in case they ask you for it in the future. If we needed to plot our focus points, remember we have that relationship. The focus comes from the C's, which we haven't looked at yet in this problem, but we can find it using this relationship, right? So C squared is equal to A squared minus B squared, and C squared then is equal to 48. So C is equal to plus or minus 4 square root of 3. Okay, I broke 48 into root 16 and root 3. So the 4 came from the root 16 part, and then you can't do anything with root 3. So 4 root 3 is a little bit more than 4. 4 root 3, oh gosh, I don't know if that's over 5 or not, but let's just pretend that it's right about in here near the 5. So those would be your focus points if you needed to have them. Hyperbolas are the last shape that we're going to take a look at in this section. Hyperbolas are the set of all points x, y in a plane for which the absolute value of the difference of the distances from two distinct fixed points called foci is constant. That's confusing. So let's go on and take a look at some pictures of hyperbolas. Flip with me to page 335. Okay, page 335 has pictures of hyperbolas. You've seen them before. All graphs of hyperbolas have two disconnected branches. The line through the two foci intersect the hyperbola at 2 points. So take a look again at those diagrams there. All right, we can see the lines drawn through. We can see A's and B's, we can see C's. Those things still stand for the same stuff as they did with our ellipse graph. So the major axis this time is called our transverse axis. Okay, so that's a little bit different, but we still have, you know, it's kind of, it just kind of bends out rather than an ellipse that bends in. All right, so you'll see a lot of similarities with this stuff that cause it to do that. So bullet number 3 on this page, the transverse axis is the line that connects the vertices. That's why you know it's always the major axis. Okay, and the midpoint of the transverse axis is the center. All right, so again, the distance is going to be 2a. Okay, because the midpoint, if that's the center, then you've got a distance a to one side, distance a to the other side, or a distance of 2a. Standard equations of the parabola with center at the origin. Notice the similarities here from the ellipses. There's two situations again. Sometimes our transverse axis will be the horizontal, and then we have the form that you see there. Step 2, if the transverse axis is vertical, then it takes on the form that you see there. Okay, notice that they're identical except that the y squared and the x squared change spots. The vertices, like I said before, are A units from the center. The foci are still C units from the center. A, B, and C also again have a relation. So if you know 2 of them, you can find the third. This relationship for the hyperbola is B squared equals C squared minus A squared. I threw in a couple of pictures that I stole off the internet that had all of these pieces put together so you can take a look at it. Now, one thing that we haven't been talking about yet, it'll come up in our one more slide, are these right here. Those are our asymptote lines, and we'll talk about them in a second. All right, but you can see your vertices, 0a and 0 negative a. This is a vertical transverse. You can see your focus points that are in line with those vertices. Okay, and you can see that standard form that we were just talking about there. Okay, give you a couple of seconds to look. Let's flip to the next slide. I also put one here if the horizontal transverse or the transverse axis is horizontal. And again, you can see the same kind of stuff here. Okay. So again, those vertices, they give you plots that are, or points that are on the curve, and then those asymptotes, which we're going to talk about here next, keep us from getting too wide or too narrow of a curve for our hyperbola. All right, finding the standard equation of a hyperbola. If you have the foci again, you have the c. If you have the vertices, you have a. So you can put them into the b squared minus c squared, or b squared equals c squared minus a squared, and solve for the b. Then once you have b, the standard form of the equation needs a and b, and you can put them in and simplify. So let's take a look at checkpoint number 6. Find the standard form of the equation of the hyperbola with foci at 0, 6 and 0, negative 6, and vertices at 0, 3 and 0, negative 3. All right, so what do we know so far? Well, if these are our foci, c is equal to 6. If this is my vertice, a is equal to 3. So now I can use that relationship and figure out b. b squared is equal to c squared minus a squared. So we've got 6 squared minus 3 squared, which is 36 minus 9, or 27. Okay. If we were to go on and solve for b, we'd get square root 9 times square root 3 if we broke our square to 27. Maybe I'll write that step in. Hang on. I'm not going to skip that step. Plus or minus root 27, which is plus or minus root 9 times root 3 if we break it. The root 9 solvable. The root 3 you're stuck with. All right, so there's our flat out value of b. So in our problem here, okay, if you're, let's give yourself a really quick sketch here to figure out our vertical versus horizontal. Your vertices are 0, 3 and 0, negative 3. So this has to be that transverse axis. Okay, so this one's going to be a vertical one. So the format that we're going to use is this one. Y squared over a squared minus x squared over b squared equals 1. Now it's just a matter of plugging in our stuff. So if a was 3, we have y squared over 3 squared. B we just found was 3 square root 3. And there we go. There's our standard form. Again, they don't suggest that we actually do that squaring and come up with regular numbers, because if they would turn around then you and ask to sketch this, you would need the 3 and the 3 root 3 more than you would need the 9 and the 27. To help sketching the hyperbolas, now where those asymptotes thing that I mentioned come into play. Each hyperbola has 2 asymptotes that intersect in the center. The axis that runs from negative b to b is called the conjugate axis. All right, so the major one on the hyperbola was called the transverse axis. The one that runs from b to b is called the conjugate axis rather than the minor. The asymptotes form the diagonals of a rectangle with dimensions 2a by 2b. We'll show you that on a diagram in a second here. Asymptotes of a hyperbola with center at the origin. Again, they're going to depend a little bit on whether or not the transverse axis is horizontal or vertical. So the asymptote equations are going to be y equals b over ax, and y is equal to negative b over ax if it's a horizontal transverse. If it's a vertical one, then it's going to be y is equal to a over bx, and y is equal to negative a over bx. So let's sketch this hyperbola. First thing, notice here, we're not quite in standard form. So I'm going to rewrite this one so that we do have a square of something underneath our x squared. Well, x squared is over to 1, so 1 can be rewritten as 1 squared without changing or hurting anything. It's already equal to 1, so we're now in standard form. Now, since the, let's see, since the first term, this one is smaller than the first one, we're looking at a horizontal transverse, because that's got to be b. Okay, a is always bigger, so if x squared is over the b one, then we have a horizontal situation going on. So we can figure out let's second here. I think I just told you something wrong. Oh, a is always in the front on a hyperbola. That's what I did wrong. Sorry, it's the x and y that swap out on this one. So no matter what, all right, erase the clock. I'm coming back. It's x squared and y squared that change between the horizontal and vertical. This position here is always a. That's right. This position here is always going to be b. So if a is equal to 1, b is going to be equal to 2, because I should have rewritten that 4 as a 2 squared back here as well. Sorry, I'm getting excited to be almost towards the end here, you guys, so bear with me. All right, so if a is equal to 1 and b is equal to 2, okay, and the x squared comes first and the y squared comes second. This is why I know this is going to be a vertical. Okay, so with the x squared first and the y squared second, this is a horizontal or a vertical transverse. All right, so let's put our A1 spot on and also -1. B is 2 and -2. Now remember that rectangle piece? This is the rectangle that they were suggesting that we draw. Our asymptotes are going to be the diagonals that go through there. Okay? And if we look at this, and we draw okay, they would come from well, let's make them. We have a vertical hyperbola, so our asymptote should be a over bx and -a over bx. Let's see if this matches. A was 1, b was 2, a was 1, b was 2. So take a look at those lines. They do have a slope of 1/2, so it goes to show that that rectangle trick works probably just as well as coming up with those asymptote lines. All right, so let's take a couple looks here at some more stuff. We haven't worked with C yet, okay, so we don't have our focus points, but I'm trying to decide if we actually need them on this one, and I think we're okay. Our vertices, if we're going to write our points of our vertices, we have 0, 1 and 0, -1 there. The conjugate axis is the b-axis, so our conjugate points at the end are 0, 2, nope, 2, 0, sorry, it's getting late, and -2, 0. Okay, our hyperbola is going to come in I believe inside our asymptotes. Okay? So again, it's not that exact of a science. We're figuring out the bounds of it with those asymptotes, and we're figuring out the vertice of it with our A's. And that's about all we need to worry about as far as graphing that in any kind of detail. One left. Let's do this. Find the standard form of the equation of the hyperbola that has vertices at negative 1, 0, and 1, 0, and asymptotes y equals negative 4x and y equals 4x. All right, well, if your vertices are negative 1 and 1, a must be 1. Our asymptotes. Okay, asymptotes, remember, are a over b and b over a. Okay, so if we have 4's there, we must have b over a. I didn't write them in the right order, but that's okay. So b is going to either be 4 or negative 4. And we can find our c. If we use our relationship, b squared equals c squared minus a squared. 4 squared equals c squared minus 1 squared. Or 16 equals c squared minus 1. Or 17 equals c squared. C is plus or minus 17 for that. Okay, so if they needed the foci, we would have our c values as well. Okay, so if we're looking at writing the standard form of our equation, our transverse is going to be a horizontal one this time. And again, you can just tell that from where your vertices are. If your vertices are negative 1, 0, and 1, 0, that means a horizontal transverse would connect them. So then I'm going to use this form of my standard. And plug in my values. So x squared over 1 squared minus y squared over 4 squared equals 1. And there we go. All right, the only way to get comfortable with these at all, and I'm still working with them too, is to do more and more and more of them. Okay, so I'm flat out making you do one of each kind, sketching it, coming up with a standard. So you've got a couple parabola problems, a couple of the ellipse problems, and a couple hyperbola problems. So use your weekend wisely, watch the video, it's a long one, and take care of doing these practice problems and a bunch of their buddies.